I left off talking about fossils and conditions that are going to favor fossils in forming. We said rapid burial so that they don't get scavenged and erosion doesn't take part of it. And they have to have a hard part, something that's going to leave the impression. If it's all just soft tissue, it doesn't leave impressions and doesn't actually leave the remains of the hard part. Lots of different fossils, like I said, that are listed in the PowerPoint. Go ahead and look at them, different types. The last and fifth type of relative time dating is called the principle of fossil succession. That fossils succeed one another in evolutionary type terms. We get into a little of geologic history next week when we talk about the history of the Earth and some of the different prehistoric animals. But just a basic, how it starts off single-celled organisms, becomes algae, and then becomes we find fish, and then amphibians, and then amphibians become reptiles. Reptiles become mammals. The evolutionary phase, how they succeed one another. So to use fossils with relative time dating, you need what's known as an index fossil, one that was widespread geographically, found all over the Earth, not just in a single spot Earth's surface, but it also had to exist for a relatively short period of time. And then you can kind of say, if you find that fossil, you know the relative time sequence of when it existed. Here's kind of an example of how different fossils only existed for different time periods, so you're able to kind of match up. And that's part of that correlation we talked about. The last type, I always said, if we want to put a numeric date to it, we have to use radiometric dating. So we could just, I'm not going to go through all the chemistry part of it, but you have them on the full slide, how the nucleus is made of protons and neutrons, electrons orbit, the atomic numbers and number of protons, the mass numbers, protons and neutrons. And then you have isotopes, which have different number of neutrons. It's the isotopes that we really need to get to. And it's because radiometric isotopes are the ones that we look at to give us the radiometric time. So radioactivity. In order to figure out how long something died or how long the fossil's been there, we need to use how long the rock's been there. It doesn't have to be living. We have to use radioactivity, which is the spontaneous decay of the nucleus. It's going to do it on its own. It's going to start to decay. And in doing so, we need to look at what the parent is, what was the original isotope, and then what does it turn into after it breaks apart. How much of the parent compared to how much of the daughter is going to tell us how long ago it either formed or it died, one or the other thing. When looking at radioactivity, we talk about three different types of decay. Alpha particle, alpha emission, which is going to be basically a large particle. A beta emission, which is an electron. And then there's an electron capture into the nucleus, which creates different atomic numbers and mass numbers. So that's kind of the key. In your book here, it talks about the alpha emission as being a helium particle that has 2 protons and 2 neutrons. 2 protons is your atomic number, your protons plus neutrons, and then makes 4. So if we know how many daughter particles till we get to from parent to daughter, beta emission is really just an electron. So, but it's not an electron leaving the cloud; it's leaving the nucleus, and that means it's coming from a neutron. So by getting rid of the negative, you're still left with the positive proton, which means the atomic number actually goes up, but the mass number doesn't change because electrons almost have no mass. And then you can capture an electron into the nucleus, which is going to attach to a proton and make it neutral. So you'll no longer have that proton sitting there as an atomic number. So you have one fewer, but then again, no change in the mass. So what we look at is how many particles go down, and it changes it from like uranium-238, which is the radioactive isotope, and it eventually, after a number of alpha particles and beta particles and gamma radiation, it eventually gets down to lead, which is stable. And that's what we look at. How long does it take to go from parent to daughter is what we need to know. Half-life is the time for 1/2 of the nucleus to decay from parent to daughter. And in order for this to work and for us to use this in timing, it has to be a closed system. Can't have more particles coming in and leaving. It has to be like a rock that's formed that it's has the exact amount that it started with and that it turned into. It's complex, as it says there. We're not going to get into it too much, but you had to be able to figure out how many half-lives there are. I did include